Hello, George Romanic here. Today we are going to explore Gaussian integral. It's an integral that has very large significance in mathematical statistics, probability, and natural sciences in general. The integral is between negative and positive infinities e to negative x squared dx. There is very particular technique how to solve this integral, so let's explore it. Gaussian integral is in the form integral from negative infinity to infinity e to negative ax squared dx, where a is a constant. Before we start solving this integral, let us see why is it called Gaussian integral. If we identify function f of x is equal e to negative ax squared, this function that you can see is here under the integral has the following shape. If this is x, and here I plot values of the function f of x, this function is Gaussian curve. Perfectly symmetric curve around the peak. And when we are asked to find the integral of this function, you can see that we are tasked to find area under this curve. And the curve goes from negative infinity all the way to the positive infinity. To solve this integral, let us call this integral I, we need to go from one variable function, an area under this curve, to two variables function, and volume under the surface that two variables function prescribes. Namely, what do I mean by that? Let us plot a nice two-dimensional plane. This is x, this is y direction. This is 90-degree angle. If I introduce vertical axis here, where I will plot the values of my two variables function f of x and y, then in one dimension, namely x, I would have this similar curve like so, but 2D function would give me, so to speak, similar curve in this direction, in the y direction, into the page. And you can see that here, with a little bit of imagination, there is this volume under this bell-shaped surface. And to solve this integral, we need to find that volume, and then we can go back and actually identify area over here. So how does one transform from one direction to two directions, namely from this to that? Well, we recognize that this variable x is the so-called dummy variable, and it can be any variable whatsoever. In other words, I could equally well write this integral I as integral from negative infinity to positive infinity e to negative ay squared dy. Or I could use any other letter, it doesn't matter. This is dummy variable that will be integrated out once we solve this integral. We can recognize something. If we now carry out procedure of squaring this integral I, that becomes I times I, then for the first I will use this integral with x. So that's integral from negative infinity to infinity e to negative ax squared dx, and for the second I'll use integral with y, negative infinity to infinity e to negative ay squared dy. Perhaps some of you are watching this saying, but come on, how could I conclude this? This would never cross my mind. And you're probably right, because you're not Gauss. You and I sit here together observing the ingenuity of greats that came before us and studying how they figured out how to solve these types of integrals. This would also probably never cross my mind, but I studied books on mathematics and now I know how to solve it thanks to the giants that came before me. With that being said, we can manipulate this integral and write it as double integral. Both go from negative infinity to positive infinity, and we have e to negative a, and I combine this by adding x squared plus y squared dx dy. Now, every time you see x squared plus y squared, something needs to cross your mind, and that something is polar coordinate system. Now, what is a polar coordinate system? Well, I have a video on it. It's another way to represent point in space. So, what we will do now, we will transfer from Cartesian coordinate system xy to polar coordinate system r and theta. And you can watch my videos on polar coordinate system, but here I will just quickly show you a relationship between these two because we need it. If this is Cartesian coordinate system xy and we have an arbitrary point A over here, then coordinates of point A in Cartesian coordinate system are this. This would be x, and this would be y component of this point A. But in a polar coordinate system, this point A has coordinates r, which is radial distance from the origin to this point, and this azimuthal angle, I usually use theta. Now, right away from here, you can see that x is r cosine theta and y is r sine theta. And from this or this, whichever one you want, you can see that x squared plus y squared is therefore r squared. If this is not clear, watch my videos on trigonometry and or video on polar coordinate system. But with this demonstrated, notice that this x squared plus y squared can be substituted for r squared. That is good. But what do we do with this dx dy? Well, if we go back here, you will notice, and maybe let me use pink for all girls that are watching this, the dx dy is a surface element dA on this surface. So this is surface element dA. Now, in Cartesian coordinate system, yes, surface element is dx dy. But what is a surface element in polar coordinate system? Well, we can easily find that. Let me replicate this polar coordinate system with x and y being here. And here we have a radial distance to some arbitrary point. This is radial distance r, and here we have angle theta. Now, to find this infinitesimal area in polar coordinate system, I need infinitesimal increments in the azimuthal direction, and let's say this is my increment in azimuthal direction, so this small angle here is d theta. And I also need increment in the radial direction, and let's say it's this. So both of these are dr, length of these radial arms. But this now represents my area dA in the polar coordinate system. You can see that this area looks very similar to parallelogram, with the difference that there is this divergence of these radial arms, but because these increments d theta as well as dr are infinitesimal, I can approximate this at first order as perfect parallelogram. Namely, what I'm saying is that from here we can say that this area dA is equal this length, which is dr, times this width over here, and this width is r times d theta. And if you really want, plus higher order terms. Higher order terms because this part over here is a little bit longer, but we neglect that. And therefore we neglect these higher order terms. Now with this knowledge, I can go back to this integral and write that my integral I squared is equal integral e to negative a x squared plus y squared is r squared, and dA is r d theta. Now what are the limits? Well, we need to cover entire 2D plane, and in polar coordinate system we can easily do it if we allow r to vary from 0 all the way to infinity, 0 to infinity, and theta to go from 0 all the way to 2 pi. But the integral d theta with the limit 0 to 2 pi is trivial, so that is equal just 2 pi integral 0 to infinity e to negative a r squared r dr. And this integral can easily be solved using substitution, but I'll show you a fancy way to do it that you can use to impress your friends in disco clubs. To do that, we will recognize that this r dr can be written as 1 over 2 d differential of r squared. Ah, look at this beauty. Because if you carry out this differentiation, you'll get this. And with this in mind, we get that this is equal 2 pi integral e to negative a r squared. R dr is 1 over 2 d r squared. Now 2 and this 2 cancels, that is very convenient. But the beauty is that this is now table integral, because I have e to negative r squared, neglecting this a, dr squared. So that would be like e to negative x dx, because both here is r squared and our differentiation is dr squared. Well, with that in mind, we can see that this integral becomes pi 0 to infinity here, negative 1 over a times e to a negative a r squared in the limits between 0 and infinity. And that I can further write as negative pi over a 1 over e to a infinity squared, but that's still infinity, minus e to negative a times 0. Well, anything to power 0 is 1, and here e to infinity is infinity, so 1 divided by infinity in limit tends to 0. And we get that this I squared I apologize, my throat is sore, is equal, this negative and this negative will cancel, and I get pi over a. But we are not interested in I squared, we are interested in I, which means that I is equal square root pi divided by a. And this is solution to the infamous Gaussian integral. This integral I, that you will remember was in the form, can only be solved if the limits of this integral are from negative infinity to positive infinity. And by only, I mean analytically, like we did it here. If we have any other limits, this integral cannot be solved analytically. And that is where the infamous error function kicks in. Error function, denoted as ERF, of some real variable x, is defined as 2 over square root of pi integral from 0 to this x for which we want to evaluate error function, e to negative t squared dt. This error function can be defined for complex numbers, and then the result is a complex number, of course. But at least for now, on this channel, we are mostly interested in real values. How does this error function look like when inputs are real numbers? Well, something like this. If here I plot x, and here I have values of error function of x, then that function is limited between -1 and 1. So here is clearly -1, here is +1, and the function looks something now like this, like an S-shaped curve. Just to give you sense of numbers, somewhere here, let's say, is -2, and maybe somewhere here is +2. We will see this Gaussian integral many times on this channel. For example, few videos from now we will use it in the derivation of a Lagrange multiplier in Boltzmann distribution of energies. You will remember that when we finished deriving Boltzmann distribution of energies, there was that pesky parameter called Lagrange multiplier that stayed unknown. Well, using this technique of Gauss integral, we can go back and explore that topic further. Until these videos, goodbye.